An interesting geometrical property of dislocation line is that the Burgess vector of a dislocation line is constant along the line. This is something quite simple and follows from the very definition of the dislocation line as the boundary between slip and unslipped regions. Remember, we have been defining the dislocation line as a line which divides the slip plane into a slip region and a no slip region. And in the slip region, there is a slip of certain magnitude and direction, and that is what is called the Burgess vector. So, the magnitude and direction of the slip is the Burgess vector, and the dislocation line itself is characterized by a tangent vector, a unit vector tangent to the dislocation line. Now, since the slip region is a single slip and it will be characterized by the same slip vector or the Burgess vector in everywhere in this region, the dislocation line also does not change its Burgess vector from point to point and has the same Burgess vector all along the line. So, anywhere along the line. So, this Burgess vector, this magnitude of direction in slip is associated with the dislocation line, and at every point of the dislocation line we have the same Burgess vector. For a straight dislocation, the T vector also is constant along the line, but an interesting situation occurs if we consider a curved dislocation line. So, if we have a curved dislocation line, a boundary between slipped and unslipped region can be curved also. In this case, the T vector will be changing along the dislocation line. So, a T vector at this point will be tangent to the dislocation line at this point, whereas the T vector at this point will change its direction, and a T vector here will be in this direction. To be consistent, the T vector along the line as it changes should have the same sense, in the sense that it should appear to follow a current flowing along the line as a wire. So, I should not flip the T as I go along this line. It should appear as if something is flowing, a current is flowing along this line. So, this is a consistent set of T. But so, a consistent set of T along a curved line, because the tangent is changing, the T vector will also be changing. But still, since we still have a single slip, the Burgess vector, whatever Burgess vector, suppose there was a Burgess vector B here, this, a horizontal vector like this, then the Burgess vector will remain horizontal at all the locations of the dislocation line, because the dislocation line is dividing the same slip and no slip regions. So, we can make a note of this, that in case of a curved dislocation line, T will change from point to point. But B will remain constant, but the Burgess vector B will remain constant. But for this to be true, t at different points should relate to each other like a flowing current. An interesting case is to consider a single dislocation as two dislocations meeting at a node. So, let us consider there is a dislocation line A B. So, it has a tangent vector T A B and has a Burgess vector B A B, and tangent vector will remain tangent as we discussed. For a straight dislocation it will remain the same, but for a curved dislocation it can change, but the B vector has to remain the same at all points. So, it is the same B vector at all points along the dislocation line. But now, suppose I wish to treat, it is possible, although it is a sort of trivial exercise, but it is possible to consider this single dislocation line as two dislocation lines meeting at n, which is a node. So, I again draw the tangent vectors. And the Burgess vector. So, for the original dislocation I am drawing for the original single dislocation, just copying what I have drawn there on the left. But as soon as I consider it as a node, remember the for application of Frank's rule, I have to take the Burgess vector, sorry, the tangent vector such that they are either both pointing to the node or away from the node. So, the original tangent vector of a single dislocation line does not satisfy this condition. So, if I consider this same, if I keep the dislocation tangent vector for the A n dislocation, now we have two dislocations A n and B n meeting at the node n, and this is a unit vector. So, I am putting a caret. So, if I take the A n tangent vector for the A n dislocation same as T A B, then for the B n dislocation I have to flip the tangent vector to be pointing towards the node like this. And you know that if I change the B n vector, if I flip the tangent vector, then the Burgess vector will also get flipped. The Burgess vector will remain along the same line of the same length, but will change its direction. So, this is now my negative of B A B. whereas the Burgess vector of an will remain the same as the original. So, this exercise reminds you of two important conditions, that if you consider a node, then the tangent vector should be pointing to the node. All the tangent vector of the all the dislocations meeting at the node, they should be pointing towards the node. So, we have done that exercise here for the Bn, we have flipped so that it is pointing to the node. An anyway is pointing to the node. Then you can see, now you can apply the Frank's rule. So, the sum of the Burgess vector, all the Burgess vector at the node, and here there are only two dislocations. So, I have two Burgess vector, so which I add. So, one dislocation is a n. So, I have sum of these two dislocation b a n and b n. You have seen that b a n is same as the original b a b, but b b n became negative of b a b because we flipped the corresponding t vector. So, the b vector also got flipped. So, it became minus b a b, which then obviously gives you a 0 vector satisfying the Frank's rule. So, it is possible to consider a single dislocation, any point of a single dislocation can be considered as a node at which two separate dislocations are meeting. And it is a sort of this exercise summarizes or revises some of the conventions of node, that the tangent vector should point towards the node, and the other convention that if the Burgess vector, if the t vector flips, then the b vector also flips, and the third, that the sum of the Burgess vector at the node should be 0, which is we have already introduced as Frank's rule.